Well, lads, this video is going to go through the 2014 higher level short questions. First question there tells us the drawing shows the projections of a set of soccer goalposts. A ball is positioned at P for 2 penalty kicks during a World Cup match. The ball travels in a straight line and hits the net each time. Part A. The line PS in plan shows the start of the flight path of the ball for the first penalty kick. The ball crossed the goal line at a height that is halfway between the ground and the crossbar. Draw the projections of the full flight path. So we're told basically the ball travels from P, goes along this direction here, and it's going to hit the back of the net. And then we're also told that where it crosses the goal line is halfway up from the ground to the crossbar. So you have an edge view here, so we can see exactly where it crossed the line. So what we need to do is, we need to bisect that line first. So take a distance greater than halfway and swing an arc each side. So you can see there, it's going to cross at that point and it's going to hit the net exactly there. As we're looking at the end view, we can see the part position of where it's actually going to hit the net at that point there. All we can do then is, I'll just mark that as S, we can drop that down, we can rotate it around into our plan. And we can see where the ball is going to stop then in plan. So if we take it along PS, stops at this point here, and then taking that up into our elevation and across, we get S there as well. And I take P up as well, it's in the very centre of the goals. And now we have the full flight path for PS for the first penalty kick. For part B then, similarly, the line PT, which makes an angle of 15 degrees with the ground, shows the flight path of the ball for the second kick. Draw the full projections of the full flight path. So basically, it's going to go along at that angle there. It's going to go 15 degrees. So the only way we can see the actual true 15-degree inclination is by looking in perpendicular to where the ball is kicked. So you can see along there, if we look in perpendicular, we can see it at 15 degrees. So what we need to do is to get our protractor from point P. There's your 15 degrees from where the ball goes off the ground. So that there is our 15-degree mark, and it's the back of the net at that point there. So what we do is extend that up perpendicular as well, and that gives us the height of the ball when it hits the net. So we take that height and we can apply it to where it hits the back of the net there. And you can see the ball hits the back of the net at that point there. And we take T across. And we take T up then from here. So there's T where it hits the back of the net there. And there we have the flight path of the ball when it hits the back of the net going out towards T. So there it is, inclined at 15 degrees. There's the height that hits off the ground, so we have to look in perpendicular to see that height. If we look straight in here, we can't see that true inclination. We have to look in perpendicular to it. Then for A2, the 3D graphic below shows a piece of play equipment from a science museum. It includes a truncated hexagonal prism. The drawing on the right shows the incomplete projections of a similar hexagonal prism, which is being cut by the oblique plane VTH. So you can see there, vertical trace and horizontal trace have cut the object there. An auxiliary elevation is also given, so giving us an edge view. So we can use that edge view to plot the rest of our points. Part A, complete the plan and elevation of the cut prism. So you can see there, works out to be at 60 degrees. We take down all of our points. So the top 2 points there are located here and here. Just draw that in heavy as well. Next 2 points, we're already given the line, touches off here and here, and the bottom 2 points touch there and there. So all we need to do now is connect those together to get our plan. So that's our plan view of our cut. And then take our points straight up. So the top 2 are those 2 points there. And they hit there and there. The middle 2, just extend our line. That's given as this point. And this point, which is already given to us. And the bottom 2, one's given there, and the other one we now have is there. We can connect those together. Let me just extend this line here and put in my hidden detail in both my views, and that'll complete part A for us. So nice and simple. Part B then, determine the true shape of the cut surface. So basically, what does that cut surface actually look like? So there's 2 methods you could do it. One is where we take an auxiliary, where we look in perpendicular to there, but there's not enough space there, so they're kind of hinting at us to basically take a rabated view. So basically where we take a hinge point and we rotate it around onto the ground and then take our view down into our plan. So you can imagine if this is our shape here, what we're doing is, there's an edge view. We rotate it around till it's in line, take it down and put it flat down, and that will give us our true shape. That's basically what we're trying to do. So, because we have an edge view, we have a true length from top to bottom, so we can use those. Rotate this around here, and this around here. And what we can do then is take these down into our plan. These 2 are already touching off the ground. There's our hinge point. So I'll do is just label it 1, 2, 3, 4, 5, and 6. 1 and 2 are here. 3 and 6 are there. And there's 4 and 5. So 1 and 2 we already have. Take out 3. Gives us 3 there. If we look, 3 is on that line. 6 as well. 6 is on this line here. And then 5 is there. And 4 is there. All I need to do now is connect them all together. So 1 to 6, 6 to 5, 5 to 4, 4 to 3, and then 3 to 2. And that gives us our true shape. A3 then. The 3D graphic below shows a tagine, which is the type of clay oven frequently used in North African cooking. The drawing on the right shows the incomplete elevation of the tagine. The upper lid is based on 2 semi-parabolas, which are inscribed in rectangles, and the lower dish is based on a semi-ellipse. Part A. V1 and V2 are the vertices of the semi-parabolas. P is a point on the semi-ellipse. Small portions of 2 of the curves have already been drawn. Complete the elevation of the tagine. Show clearly how the exact length of the base is obtained. So basically, when you draw your ellipse and you extend your base, you're going to find exactly where it hits the semi-ellipse at the bottom. So we draw our full ellipse and we extend our baseline out. So they've already shown you there to find 1 point. Taking a line out where it hits the outside circle, take it up. Where it's the inside circle, take it across. So your major and minor circles. So I'm going to do the exact same with the rest. I'm going to use my 60-30 just like we would in Junior Cert and drawing ellipses in general. So 30/60 out both ways. And then taking our points up and across. And then we just draw our curve. So I'll draw lightly first, then extend my base out to hit it, and then after that I can draw in heavy where the curve stops and starts. Just like that there. Then for the parabola, you can see they're showing us that all of our side points here, which are on the base, because the vertex up at the top here, the top left, they connect there. So what I'll do is, I'll take a line out an angle there, mark off 5 distances. So 1, 2, 3, 4, 5. And I connect those back. You can see this one already lines up there. And they're showing you they're all connected to the vertex there. So all of these points connect to the vertex as well. And then I'll divide my base as well into a number of equal parts. So same as the side. Make it 5. 1, 2, 3, 4, and 5. Connect that back to there. The last one connects there as well. And they'll just go horizontally to hit my points I've already marked off. There's my first, second, third, and I already have my fourth one given to me. Drawing my curve like that. And then all I need to do is, instead of redoing all that on the opposite side, take my points across and then mirror them. So from the center, that point there moves to there. This point here moves across to there. Third point goes there, and my last point goes to there. I do the same thing again, just draw my curve. And there, that's part A complete. And then part B, draw a tangent to the curve at point P. So we're drawing a tangent to a curve given to the point in the ellipse. So the point is on the ellipse. So what I need to do is get my focal point first. So remember, take half the major, swing it from the minor. That gives me F1 and F2. Connect them back to P. So we're applying a principle we would have learned in Junior Cert. And we bisect the angle in between. Connect that back, giving us our normal. And we know when we go 90 degrees to our normal, we always get a tangent. And there's our tangent then drawn. The last one, A4. The drawing on the right shows a partially complete perspective projection of a tennis court. Part A, the position of one of the vanishing points VP2 is shown. Locate the other vanishing point. So we know from setting up the question that our vanishing points are located parallel to our edges. You can see there from the spectator, we go parallel to this edge here. So to find the other one, we go parallel to this one here. So it's just basically a vertical line. Where it hits there, you can see it goes back perpendicular. Sorry, from here, it goes back perpendicular, giving you your vanishing point. So this line here actually works out to be 60 degrees. So what I can do is go back 30 degrees there. That gives me vanishing point 1. So that angle there is perpendicular. Part B, complete the perspective projection of the tennis court and the net. So you can see they've very started it for you. They've shown you that some of the points you connect them back to S, and where they hit the picture plane, it gives you a new width. You take that back then as a result. So for the opposite two corners, you can just take them back to S, like that there. And where they hit the picture plane, goes down like that there. And this one goes down here. And we join them back to our vanishing point on the right. So now we have the length of our tennis court there. And the back point goes back to here. And you'll see that these connect through together as well. Just put that out of the way. Just like that there. Now our two lines, there and there. Same idea again. Join them back to S. Or they hit the picture plane. Take them back. So they hit here and here. And you'll see that when I join them through, get your 2 points there and there. And same the opposite side. Join these back through S. We did the picture plane. That gives you your front one there. Your back one goes through there. And you'll see once again, both points will pass through each other. And the actual vanishing point. Giving your line there. And then all we need to do is take one of these down, just save a bit of time. You don't take them all down. Where that connects back to the spectator. That point there goes out parallel, and that gives you, sorry, take this one here as well. Take that back to the spectator, out parallel there, and we join it back through the vanishing point, gives you your line there, which gives you that point there as well. You can see the line up automatically then as well. Then part C, determine the true height of the net. So basically, you can see the net is not touching the picture plane at all, therefore it can't be a true height. So what we need to do is, we need to extend the net out, touch the picture plane. It's almost like we move the net across. Where it touches the picture plane, we take that down to the ground line here. So that's our ground line. So you can see there, the only corner that touches the ground line initially for the picture plane is that corner there. We've now moved the net over and made it look like it's touching the ground line. The vanishing point you'll see when you extend it out, on the ground there, and we extend the net out, we can now see our true height there as a result. Put that down as h for height. That gives us our true height. So basically we have to extend it out first to hit the picture plane so that it appears the true height. We take it down to the ground line, and then we can join our vanishing point through it to get our height then as a result. So hopefully that video helps anybody who's been stuck on any of those questions.